Hello, my name is Rez, and I'm a professional game programmer, and I do electrical engineering stuff as a hobby. This is day 5 of our robot advent calendar. This is the technical talk. So I want to talk about something that this thing briefly mentions in here, where it says that we can use this as a sort of electrical, like electric generator, which is true. Basically, all that we have with an electric generator, I talked about how motors work, and how there's these like two magnets and this like coil with this like brush that's sort of here that's as current flows through this coil, it creates this magnetic field which expands and collapses, and so on, basically causing this sort of north and south pole. These are fixed magnets to rotate this thing around. This, of course, in turn is tied to the actual like thing in here that's turning, and and that's how that works. So we're using electricity. We're using the flow of current here to generate a magnetic force, magnetic field, which is then driving a physical thing. But it works exactly the same in reverse. We can use a physical force or something to basically create these to force these magnetic fields, right? So I can just I can literally hand crank it. That will actually cause current to flow through here. It's just the magic of electromagnetic force and just electromagnetism in general. And we can watch it. We can watch it happen. This is how generators actually work. So if you have a river with water flowing in one direction, and sitting in this water, you have these sort of like blades that come out. You've got another one up here, right? So you've got this like whole water wheel thing. So as the current is flowing, as the water is flowing, it's causing this thing to move. And this has a bunch of blades on it. Windmills work the same way. So we've got this windmill that's attached to the ground here like this, right? And it comes up and it's got these blades which catch the wind. I'm not an artist, so forgive my drawings. But they catch the wind, causing this to turn, and it's doing exactly what we're doing here. We're just using, I'm burning an infinitesimal amount of calories rotating this thing, and that's causing current to flow. So we can actually measure this. So you might notice these probes that are hooked up here again. So this is my oscilloscope again. So if we go back up to the oscilloscope, which is here, we can actually watch this happen. So I just have the yellow trace at this point because I don't need anything else. And I've set a thing. I'm just going to set this to trace mode. What it's going to do is it's going to stop as soon as it detects a voltage below a volt. And there it is. There's my voltage. And it's a waveform, so it's generating essentially alternating current. But this is building and collapsing of the magnetic field. That's what we're seeing here, and that's creating a voltage. So that's the creation of a little generator. And I'm not going to do it anymore because I don't want to keep screwing up this thing. The other piece that the book talks about is this guy right here. So this is a resistor. This resists the flow of current. The best analogy, this sort of classic analogy, is if you imagine that you have a sink, and that connected to the sink you have a faucet. And connected to that, you've got the little handles for hot and cold. And let's say I turn this cold handle and I turn it to about 50%. Well, water is going to flow from there. If I turn it further to all the way, more water is going to flow. And so what we're doing in this analogy is we are changing the amount of resistance to the water pressure. So we have a constant water pressure that's against this faucet. that would essentially be our voltage. We have a resistance to that, right? So depending on how much I've turned this knob, I have a resistance to that. As water flows, we call that the current. And the combination of current and voltage gives us our power. And this gives us the four major things that we have in Ohm's law, very briefly. The way that I always saw it written and that I liked was as this triangle where you had V, R, I, and you had P and V and I. This is how I've always seen it written. Whereas things adjacent to each other are multiplied and things above, this is a division. Thus, you can say that to get the total current, current is with an I. I don't actually know the history of that. There probably is one that is interesting and useful, but I don't know what it is. C in electrical engineering is for capacitance usually. But anyway, so if I take the voltage and I divide it by the resistance, that'll give me how much current is flowing through there. So for example, if I have a 9-volt battery over a 1K ohm or 1,000 ohm resistor, I will have 0.009 amps or 9 milliamps flowing through that circuit. That's basically it. And so, I mean, it's called Ohm's law, and that's our bread and butter, and we do it every single day, constantly. That's how we're trying to figure this out. In fact, that's why they chose this particular value for the resistor, because they wanted to calculate. They know 4.5 volts is going to be going through the whole circuit, and they know what these values are. So they need to know what this guy drops, which looks like it's about 1.5-ish or 1.7-ish, 1.8. And they know what this is. So if we did the math here, and we say, we'd have to say 4.5 minus the LED's voltage of approximately, I feel like it's about 1.8. I'm going to call it 1.8. That gives us 2.7. So I'd expect about 2.7 volts to be across that resistor. If I then divide it by 1,000 ohms, which is what they've given us, that means I'm going to have about 2.7 milliamps flowing through the circuit. And then again, you can look at the data sheet and figure out how much needs to be there in order to have the LED actually light. And just to verify the math here, is that right? That looks about right. If I turn this on just normally, and I press this button, I can see that I have about 1.87 volts across this resistor. So it looks like I was incorrect about my actual calculations. So let's pause this for a minute and see what the resistor is actually, or sorry, the LED is actually dropping. So 2.6 is what it wants in order to be able to really, that's what it's, if you give it all you've got, that's what it's going to drop. So if we go back to our map, right, we've got, what did I say, 2.6. So this thing's going to drop 2.6. So if I then go back to my calculator, and I say 4.5 minus 2.6, that gives me 1.9, which is about what we were seeing before. Now I can do the math, and here we go. We're getting, almost 2 milliamps of current. Again, it's going to depend on what this LED wants. But let's look at the current. And there it is, 1.87 milliamps. And I calculated 1.9. So that's about right. That's pretty spot on. That's it. So that's how current and all that kind of stuff works, and that's how we can use this as a generator and what's going on. Now let's talk about the next piece of this. We also talk about the resistor itself. And I want to show what that resistor looks like. Once again, we pull out open circuits. I love this. I love this book. And we look at a resistor. So here we see the actual resistor. So there it is. In some circuit, this is how you see through-hole resistors anyway. What it actually is it's a carbon filling. It's not a filling really, it's a carbon sort of strip. Carbon is a sort of semiconductor. It's a way of resisting the flow of current. It doesn't flow as well as, say, a copper wire. And so what we do is we have this kind of thing. So we've got this, these are the electrodes themselves. So this is what's coming out. These are these metal pieces here. And then inside of here, we've got this like metal cap. This is again part of the electrode. There's a ceramic rod. Now the ceramic rod is not among our conductive materials. It is very much an insulator, and that's its purpose. So there's this strip. It coils around it. And this is a carbon film sort of coating. This is our this is our actual thing. It's connected here and it's connected on this side. This is the thing that's actually resisting current. So current comes up here, goes through here, goes through this sort of coil thing, and then heads out there. Here is a photo, a high-res photo of it. And this is the ceramic piece. Now, you can't really see it super well. But you see how there's this like very slight groove here? Here's another one. Here's another one. And they're on this side too, that they're kind of harder to see there. This groove is this carbon coating. So it's quite thin. The makeup of it, how thick it is, all that stuff, that determines the resistor's properties. What's what I'm looking for? Like how resistant it is, right? What the value of the resistor is determined by this. Also the wattage and stuff like that as well. As current flows here, this is going to heat up. Okay, here is another image of it showing sort of just this. So this is like a sort of, I guess, resin or epoxy. Here it is with all of that gone, but you can really see this is the carbon. These are the carbon strips basically, and then you've got your ceramic rod in there. So yeah, that's basically it. This is our spiral sort of groove thing. There's tons of different types. There's a film resistor like this. There's the power resistors. You can see a picture of one here. And in fact, here's one in general that I just have. It feels like chalk. This is a 10 watt, 1 ohm resistor with a 5% tolerance. That's what all this means. So it can handle 10 watts, which is a decent amount. I bought a few of these. I think I went to Fry's back when that was a thing, and I bought 4 or 5 of them. And I needed a very high precision resistor. This was the best that I could find on relatively short notice. So I bought them all and I just tested all of them and said, okay, which one is closest to tolerance? But I needed a little 1 ohm, very high powered resistor. That resistor actually is in this little guy here, which is a current tester and a little tester thing that I built. So sometimes we build our own little components and stuff. Anyway, I have a bunch of them. There's other types of varying shades of gray. Here's a 32.5 ohm one. I don't know how many watts it is. So there's a bunch in here. And this is what it looks like if you were to cut it open. So there's the resistive wire in there. But yeah, just high-powered stuff. There's these, which are interesting. Here's an example of what it looks like in real life. So there's a bunch of these kinds of things. The resistor array, they're called. Here's the inside of it. Here's what it looks like. So they just keep connecting to the different elements. Surface mounts, you'll see these all over the place if you open any circuit board. And here's what they look like. So that's a resistor. They're everywhere. They're used for changing and resisting the flow of current. So that's it, and I will see you all tomorrow.